We'll be getting started here in a second.
All right.
All right, so now everybody's here, but I think I'm going to go ahead and get started. Okay, so today we need to finish whiteboarding worksheet 1, problem number 9. If you remember, we did that some time ago, but there was this word elastic in it, and at that time we hadn't talked about what that word meant. So now we should be able to do number 9, and then we're going to get started on worksheet 2. Also, I wanted to let you know that tonight, around 7:15, I will be attending a meeting that the College Board is putting on, so I'll know a little bit more information about the AP test, and I'll be able to share that with you on Thursday. I know some of you are already doing that Unit 5 on your own. That's probably a pretty good idea. Some people have even kind of shared with me what their answers are for some of those worksheets. I think some of that stuff's really doable, so like the kinematic stuff, there's kinematics again and stuff. So I would encourage you to look at some of that because I wouldn't be surprised if some of that stuff is on there. And I think some of it you can do. It's just we kind of ran out of time. Also, I think I need to let you know that I'm planning next Tuesday kind of a test quiz thing over this current unit of impulse and momentum. It's not going to be as much as a test because, it's on the computer. Um, Plus, the last test kind of killed me when it was free response and I was grading and it took forever and I'm not going to do that. Unfortunately, I know I'm being lazy, but it really literally took me days to grade that thing. And I'm just not doing that anymore. It's going to be more of it's a one-shot deal. You got the right answer or you didn't get the right answer. So I know that's not really fair for you guys. So I'm thinking about making it so that you can do it multiple times. I don't know. It's just a bad situation. But I do want to give you guys a chance to, because I think this section usually students do really well on it, and I want to give you guys a chance to um, affect your grade a little bit if you wanted to. Anyway, so worksheet 1, the problem, and I shared these with you sometime. You have to go look through your Google Drive. For problem number 9, we're doing 9A and B first. So this one says we have this golf ball that's being dropped from some height, and it says assume it's a perfectly elastic collision. And so what I'd like you to do in part A is draw a motion map. That's the one with the dots and the arrows and stuff we did a long time ago. It's kind of important you do this one because it's going to help us understand the impulse momentum idea a little bit here. And then part B, I would like you to do that to figure out the time. That's just good review, doing some kinematics to figure out what the time is. So let me give you a little bit of time to do that, and I will open up the breakout rooms for you. Krishna, at the very bottom, there should be a breakout room, and I think you are in, I don't remember where you are. Oh, and you're in room 4. So, Brandon,
We did.
Brandon, I don't have you and John in the same room, so or you're in the same room, but I didn't share the same whiteboard with you because I thought maybe some other people would be here. So
Okay.
I'm really quickly going to share with you John's folder. So if you can check, in just a second, okay?
Okay.
Okay. Okay, I think everybody's back. I'm going to share with you my screen and kind of quickly go over this problem.
Mr. Linfesti, I don't think you ever shared it with Dan and I. Because we didn't have that. We didn't have this worksheet 1. We had worksheet 2 for this.
My bad. Wait, yeah, right there it is. Worksheet 1. I've got it for you. Yeah,
Is
you
it
got.
shared with Is it shared with us?
Yeah, in fact, Adam, you even worked on problem number 8. Can you guys see the screen
Oh,
there? Yeah.
maybe we can, okay.
So it should be in your. It should say like there's a bunch of copies there. Maybe that's what's messing you up. So,
Maybe.
yeah.
I'll look again.
Okay. So, okay. This is the problem we're looking at. We have this golf ball. It's dropped from a certain height, and we're supposed to draw a kind of motion map. So here's my motion map. On the way down, notice that the dots are getting further apart. The reason why I have an uber dot here is it almost instantaneously turns around. The truth is it's not instantaneous, but it's pretty quick. And it turns around, and as it moves upward, the acceleration is the same, and so it's going to slow down, and it goes back up to the same height, assuming it's perfectly, or assuming it's elastic. So what I wanted to point out to you is this really large acceleration right when it hits, and that's the acceleration that causes a change in momentum. Okay, so I wanted to point that out to you. So it says determine the time for part B, and that's just kinematics. And so can you guys unmute yourself? What'd you guys get for the time?
I didn't see the problems.
Oh, did anybody get the time?
Like 4.5 or something.
4.5 seconds? 1 meter? Well, that'd be cool.
Oh, no,
0.45.
0.45.
Okay, all right.
Point.
So, yeah, I got 0.45. Yeah, so I use D equals VIT plus 1/2 AT squared, and the initial speed 0, so I got, yeah, 0.45 seconds. Okay, so the next one we're doing is C and D, and it looks sort of like this. And so for part C, you have to figure out what the instantaneous momentum is right before it collides. So you know momentum is equal to mass times velocity. So that means you have to do a little bit of kinematics here to figure out what that and final velocity is right before it hits. So not when it hits, because that's 0, but right before it hits, you have to do some kinematics to figure out the speed. So then you can figure out the momentum. And then part D, you have to figure out the change in momentum. So it goes from going down to going up. Keep in mind that it's elastic, so that should be able to help you out. So let me stop sharing and open up the breakout rooms again for you. Let's see. Okay. And let's see. Here and 4. Nope, not 4. Sorry, 3. So Daniel, you should get a invitation to go to a breakout room. You are in room 6. At the very bottom, there should be breakout rooms. You can put yourself in room 6. Caleb, you should get an invitation to, okay, Luke, you should get an invitation to go to breakout room 1. If you don't get that, then at the very bottom, click on breakout rooms and put yourself in room 1. There you go.
We found it, by the way.
Oh, cool. Nice. Okay. So again, I'm just going to go ahead and share my screen with you. I hope that's okay. So the next one we're looking at here is this one. So you had to do some kinematics to figure out the speed right before it hits. So can you guys unmute yourself? What'd you get for the speed right before it hits?
Is it 4.47?
Okay. Does everybody agree with that? 4.47. Any questions?
I got 4.43, but yeah.
Yeah, it's probably just rounding, or maybe using 9.8. I used VF squared equals VI squared plus 2AD. That's not the only way to do it. You can use D equals VIT plus 1/2 AT squared, and then use VF equals VI plus AT. Lots of different ways. So, and then finding the momentum, I got 0.2 kilograms times meters per second for part C. Now, the truth is, if those are your answers, we're both wrong. I'm wrong and you're wrong, because these are vector quantities and we need to have direction. I didn't put my direction on here. It should be 4.47 meters per second downward and 0.2 kilograms times meters per second downward. I know that seems trivial, but it's not trivial. It's really important. So it's a bonehead mistake I did right here, and I don't want you to make that same bonehead mistake. So downward. It's two reasons why it's a bonehead mistake. Is first of all, on an AP test, you'd probably get a point or something for that direction. But it's really kind of important for this next part for figuring out what the change in momentum is. And I think I probably kind of need to show you the previous picture. Remember the motion map, we had it moving downward first, and then we figured out that it's moving upward after it bounces. And so a lot of times students will calculate without any direction on there, and they're like, oh, they're both 0.2. And they're like, oh, I have to find the difference, so I have to subtract them. So 0.2 minus 0.2, I get 0. And that's wrong. You have to include the direction. And so I'm going to call the initial momentum downward. I'm going to say it's negative 0.2. The final momentum, which is upward, I'm going to say is positive 0.2. So it's going to be final minus initial, and that minus initial is already negative. So minus a negative is going to be positive. It actually ends up being bigger. So my impulse, J, was equal to MVF minus MVI. That's 0.2 minus a negative 0.2, and you get 0.4 kilograms times meters per second. That's why it's a real bonehead mistake if you don't put the direction, because not only will you lose a point for the direction, you're probably going to lose a mathematical, well, lots of mathematical points. So it's kind of important to include that. Any questions with that one?
Okay. I don't think so.
Okay. Now the last one here for worksheet 1. Whoops, and I'm showing you the direction. Why am I showing you the answers? That's not good. Okay, so I don't want to show you the answers. So how about we pick one here? Okay, so wait, that was the last one, wasn't it? Was that the last one?
Yeah, C and D.
Oh, duh. That's
Yeah.
why I have the answers on there. Okay, I was thinking that we had one more part. Oh, okay. So we're done with that one then. Okay, so let's see here.
No, there's an E.
There is an E.
I'm pretty sure, yeah. But
Where's mine at? Did I not have it in my file? Oh, there it is. I'm sorry, I don't know. My brain's on the fritz. Sorry about that. Okay, so for part E, we're trying to figure out what the force is now. Okay, so we've got this, we figured out the change in momentum in the previous part, and now they're giving us the time, and so now we're trying to find what the average force is. So let me stop sharing, and I'll let you guys go ahead and get in there and do that problem. Party. Okay, so I'm going to share my screen again with you. So I'm hoping that you'll kind of check your answer with my answer. Please ask questions if you have them. Okay. All right, so for this one, we're trying to figure out what the force is when this thing hits the floor. So here was the previous picture we had for the motion diagram. So here it's hitting the floor and it has this force upward. And we're trying to figure out what that force is. So try to imagine the force time graph. The truth is it would not have a constant force. It would look more like this curve here. It would kind of be kind of a bell-shaped curve. And so that force is changing. In fact, I kind of want to show you a real quick video here. It's a time warp video. I'm not sure if you're into that thing. This is a baseball that's going to hit a baseball bat. And if you've never seen time warp on Discover, what they like to do is they like to do kind of a slow motion video so you can kind of see what happens.
Are you ready? I'm all set up. Okay.
At 10,000 frames per second, we can see the regulation.
So you can see there, the ball is actually distorted. It's not an instantaneous thing. It happens over a certain amount of time. And you can almost think of this ball as acting like a spring. So as it starts to get squished, that force is going up, up, up. And then when it has maximum compression, that's when it's going to have that maximum force. And then as it starts to come back to its normal shape, then that force starts to diminish again. So let me make this video go away. And so really, it's going to look more like this U-shaped curve. Now, it doesn't give us an equation for that U-shaped curve, so there's no way that when we're calculating the impulse that we can do any calculus to integrate and find that area. However, could you please look at the dotted rectangle I have there? That dotted rectangle has about the same area as the U-shaped curve. And so the height of that rectangle is what I'm calling F average, the average force. So you could pretend as though it has some constant average force here. And so then you can use the impulse momentum idea of force, the average force times time equals the change in momentum, which we calculated already, 0.4. And then plug it in, and I got an average force of 1006. Please understand that the maximum force would actually be much more than that. So what that means over here in my motion diagram is that that normal force, which causes the impulse, is not a constant normal force. In fact, when it first starts to touch it, the normal force would be 0, and then the normal force would actually have some maximum amount, be much more than what the gravitational force is. Okay, so any questions on that one? 1006 newtons. Okay, no question?
Well, I mean, mine was off by 6 newtons, so I don't know why that was like that.
Did you have your change of momentum is equal to 0.4?
Yeah, I did. Well, I mean, mine was off by like a little bit because I used 10 as gravity.
Oh, that's why then. That's totally why. So,
okay.
Yeah. Okay, so the next one we're getting ready to do then is, so we got worksheet 1 done. Now we're going to start doing worksheet 2. This is another one I shared with you here recently, and I didn't want you to divide and conquer it. So let's see here. Worksheet 2. Oh, I need to talk about this one a little bit because it's a little confusing here. So problem number 1. The reason why it's a little confusing is because it has these momentum charts, and I need to explain how to use these momentum charts. First thing I want to do is kind of read through the problem and kind of draw a picture. So here we have this railroad this train being assembled in this railroad yard, and we have this empty car that's moving at 3 meters per second, and it hits a loaded car. So here's my initial picture. So the blue one's the empty one, and it's going to hit this loaded car, the red one, that has some lumber or something in it, and it's just sitting there. Afterwards, it says that they're, let's see, they couple together, so they're going to be moving together, okay? And so, could you guys unmute yourself for a second? What kind of event is this? Don't shout it out yet. Let me give you the options. What kind of event is this? Usually we use the word event to talk about right there when this happens. Is this called a collision? Excuse me, a explosion? Is this a elastic collision? Is this an inelastic collision? Or is this a perfectly inelastic collision? Which one is this?
Perfectly inelastic.
Isn't it perfectly inelastic?
That's it. They get stuck together. This is perfectly inelastic. So I really recommend that you actually draw pictures like I have here. I know you think that there's no real sense in it. The truth is this picture is an equation. It's a visual equation. It shows me that over here on the left, I have a certain amount of momentum. Here I have a certain momentum, which is 0. The total momentum over here on the left-hand side has got to be equal to the total momentum over here on the right-hand side. That's an equation. This up here is also a visual equation, and so I kind of want to show you how to use this. So in the beginning, only the blue car has momentum. And there's two quantities that define momentum, mass and velocity. You can see that the blue car has a lot less mass than the total red and yellow combined. In fact, if you look at it, the mass of the blue car is 9,000 kilograms. The mass of the red car is also 9,000, but it has 55,000 kilograms of lumber on it. So the red and yellow combined is about 6 times more massive. Okay, so what I'm going to do is I'm going to say that initially we've got this blue car which has very little mass. It's moving at 3 meters per second. Notice the width of my blue line here is how long it is horizontally is 3 units. That corresponds to velocity. It's moving it, I'm going to say, in the positive direction. It's not very wide though. If I was going to make one for the red and yellow combined, let's say the red and yellow is actually just red. Let's make this red too. This red. Then it's about 6 times the height of the other one. So if I say that blue one is about 1/3 of a square, then this one's going to be it's going to be about 6 times more than that. So it's going to be 2 squares high, 2 squares high, but it's not moving. So its depth, its width is going to be 0. And I can't really make it 0. So I'm just going to make it go away. So it has 0 width this way. It's 2 units this way, but it's 0 this way. So I want you to look at the total area there. That area represents the momentum. The final momentum has to be the same area as this, but it's going to be 1/3. Oops, there we go. Let me move this one. It's going to be 1/3 of a block wide, and it's going to be 2 blocks wide. And I have to make it so that when I add these together, I get a momentum, I get a total area. So imagine painting an area. Oh my gosh, I can't get it to line up. Imagine painting an area of a room. It's got to be the same area as this over here. So I think I'm close, but not exactly. I think it's a little bit less than that. That's how this helps you. And so now I could actually figure out what the velocity is. So it looks like it's less than 1. If I had to guess, it's probably less than 1/2. Okay. So what I would like you to do, I don't need you to do the, I don't need you to do this table up here because we did that together. In fact, we're really not going to use this table at all, this conservation diagram. Although I will say this, if students are having a hard time and they're not getting a mathematical answer, then that tells me that you probably ought to start doing some of these conservation of momentum diagrams, okay? So all I really want you to do is I want you to write the equation and I want you to solve it. Okay, so let me stop sharing and open up the breakout rooms.
Or not.
Okay, instead of having one of you share your screen, I'm just going to share mine because usually students think these are pretty easy, and so I want to go through them a little bit quicker. Please, though, if you got this wrong or if you're not understanding something, you stop me, okay? So I hope that's okay. So let me share my screen with you. Okay, so I've got my picture down here, and I kind of want you to look down below the picture. Notice I have PI equals PF. That goes along with the picture. PI is the stuff totally over here on the left-hand side, and PF is everything over here on the right-hand side. And so the equation right above, then, I have my initial momentum, which is 3 times 9,000 plus 0, because this first one, or this red one's not moving, equals 9,000 times V plus 6,400 times V. They both have the same velocity because they're stuck together perfectly in elastic collision. Okay, and then I solved it and I got 0.37 meters per second. Now, again, these are vector quantities and I really should have put a direction, but the truth is in this problem, it doesn't say a direction. So I'm okay here. So, but be careful because a lot of times they'll have a direction in the problem and you need to put a direction. A positive, negative is not good enough, usually. Any questions?
No, I don't think so.
Can you give me a thumbs up if you got the same answer, if you agree? Thumbs up at the very bottom, there's like a little reaction thing. Okay, so everybody's all right? Anybody have any questions? Looks like everybody's okay. All right. Okay, then the next one we're doing is problem number 2. And number 2, I think I again want to help you do the momentum diagram because students usually are kind of confused about it. So initially, the astronaut is just kind of holding on to this oxygen tank. But what's going to happen is they're going to push it away from them. So the oxygen tank is going to fly in one direction. And because of that, because momentum is conserved, the astronaut is going to recoil in the opposite direction. So first of all, could you unmute yourself for a second? Unmute yourself, everybody, please. So the question is this: what kind of event is this? And here are your options: explosion, elastic collision, inelastic collision, or perfectly inelastic collision.
Explosion.
Yes, this is an explosion. That's right. So before the explosion, they're not moving, so the momentum would be 0. I'm going to have blue represent the astronaut, and it's so tall because their mass is 80 kilograms compared to the 10 of the red, which is the oxygen tank. So it's 8 times taller. But initially, neither one of them are moving. So if I were to put them on here, they would have a velocity of 0. And so their horizontal width would go to 0. And so I'm actually going to just simply say they're not there. Okay. Afterwards, the oxygen tank is going to move to the left. I'm going to say that's negative to help me do some calculations here. And it's moving at 2 meters per second. So notice there's no area over here on the left. I see nothing. That means the total area on the right-hand side has to be 0. Well, that red one, since it's moving to the left, or it's horizontally to the left, that's really negative area. I need to have a positive amount equal area to cancel it out. And so the width of this, I should say the height of this blue one is 2 units. And so I have to get exactly the same amount of area. So keep in mind that the height of this red one is 1/8 of the blue one. So, and it goes, so it's 1/8 times 2 units. So it's like it has an area of -1/4. I need this blue one to have an area of -1/4, and it has a height of 2. So that's how it's kind of helping you write this mathematical equation. So all I want you to do on this problem, you don't need to draw the diagram like I just did. All I need you to do is write the equation and then solve it for the speed of the astronaut. So let me stop sharing and open up the breakout rooms. Okay, I know I didn't give you a lot of time there, but again, students usually think these are pretty easy. I'm going to share my screen with you, all right? So I went ahead and drew a before and after picture, initial and final. So this is before the explosion. And then after the explosion, the astronaut goes in one direction, the oxygen tank in the other way. So that helps me write the equation. Before, initial, equals final. Initially, it's not moving, so initial momentum is 0. The final momentum would be mass times velocity plus mass times velocity. And then down here, I did the math. And so I'd have 0 equals 80 times v plus 10 times 2, or you can even do 10 times -2. It doesn't really matter. And I ended up getting 0.25 meters per second, but I need to say something about direction. And the only thing I can really say is it's in the opposite direction of the tank. All good? Thumbs up if you got the same answer. Down at the bottom, yeah, okay. So we're all good? Any questions? Okay, so the last one we're gonna do, any questions?
No, I don't think so.
Okay, the last one we're doing is number 3. And again, I kind of want to talk about the diagram up here. So we have this tennis player and they are returning a serve, and we're supposed to do some calculations here. The truth is there's only one object here, and that's the ball, the mass. So you might be thinking, how can I do a conservation momentum chart? I mean, you really can't do conservation momentum here, but it can still be used to figure out the impulse. So I'm going to have the, excuse me, I'm going to have this box here, this blue box, be the momentum of the ball. And so initially it's moving at 30 meters per second towards the tennis player. So I'm going to say that's in the negative direction. So I just have it 1 unit tall and I have it 3 units wide. Afterwards, the momentum is, let's see, it's going to still be the same height, but now it's only going to be 2.5 units wide in the positive direction. And so the reason why I think sometimes this is helpful for figuring out the momentum is because in this case here, I could see they're in different directions. This one's negative, this one's positive. So if I want to figure out what the total change of momentum is, it's going to be the final, which is positive, minus the initial, which is negative. So minus the negative, that would be positive. So it's actually going to be bigger. Okay. So all I really want you to do for this one is do part B, where you write the impulse momentum equation, and then C, solve for the force. Okay, so let me stop sharing and open up the breakout rooms. I know I didn't give you a lot of time on that, but did anybody get an answer? Can you unmute yourself and say your answer if you got it?
I did not.
Nobody? Anybody get it?
I got minus 11.
Minus 11.
I
Anybody
got
else?
2.
2.
I got 22 now.
22. Okay.
22.
Okay, so let me share my screen with you. Okay, so the impulse momentum equation looks like this. So it'd be force times time equals mvf minus mvi. We don't know what the force is, but we do know the time is 0.5. For the mvf minus mvi, we have to be really careful because they're in opposite directions. That's where a picture kind of helps out. That's where this momentum diagram helps out. So it'd be 0.2 times 25 minus 0.2 times a negative 30. So we end up actually getting a bigger number. And so, yeah, I got 22 newtons as well. So people who didn't get that, do you still have questions? You see where you made a mistake, hopefully. All right, so that's the last one we're going to do. I need to talk about what I want you to do for homework. I want you to keep on working on that worksheet 2. There's only 3 more problems. Please don't divide and conquer. Kind of maybe create your own Zoom with your partners and finish it up. I also want you to, by hand, to work on worksheet 3, and the way you get that is download it from right here in this unit. And open this up and just on paper, you know, start working these out. These are similar to the ones we were just doing. And again, I'm not so key in on the diagram. I don't care if you use it or not, unless you're absolutely not getting this. Like all these problems we've been doing so far mathematically, you've been getting the wrong answer. I'd really recommend you using a diagram. But worksheet 3 is very similar to the worksheet we just got done. Okay, so that would facilitate our whiteboarding. The other thing, I would like you to do this attendance quiz, which is over the whiteboarding we just did today. So let me share the code for that, the access code. The access code, and these are all lowercase letters and numbers. E is in elephant, P is in prize, 5, Z is in zebra, 5, 6, Q, Z is in zebra, D is in dog. E, P, 5Z, 56Q, Z, D is in dog. And before we leave, I would like to kind of get a picture of you guys for attendance purposes. So if you could maybe briefly turn on, everybody looks beautiful. You don't need to change everything, man. I just love the hair, the lustrous hair. That's awesome. Need to get a haircut. All right. Count of 3. I'm going to get your picture. So 1, 2, 3. Okay. Thank you very much. And that is it. See ya.
All right, thank you.
Bye.
Oh, Mr. Lundfester?
Yep. Yes.
Do you think you could open the My AP, like FRQs for the units that we have, like the actual AP test is still going to be over?
I can. The reason why I didn't open, I mean, I can go in there. I didn't want you to be overwhelmed. There should be some problems in there that are, what did they call it? There should be 3 that's available for you to do that are just like the ones that are supposed to be on the test. Are those not open? I thought those were open.
I thought I just looked and I didn't see any open, but I could be wrong.
Now, do you have this lockdown browser thing or something? I don't know anything about that. Do you have the lockdown browser? Because my understanding is maybe you need that for the lockdown browser.
Oh, I don't know. I don't think.
Let me go in there. Let me go in there real quick so I can. So can you stay on for a second, and then I'm
Yeah.
going to open up the classroom from my end of it. That way you can see what I'm talking about for the problems.
Mhm.
Let's see. Okay, here we go. It took me a while to find them, so I'm hoping I could find them quicker this time. Let's see. All right. So let's see. so where were they at? Dang it. I hate this thing. I mean, this is absolutely the word. I can't remember. Oh, was it in question bank? Was that it? Question bank. And then assign. Is that where it was? Was it progress? Okay. So, oh, I'm not sharing my screen with you. Duh. Okay. So let me share my screen with you. All right. Let me show you where they are, and then I'll try to get back to it again. So there's this little bullseye. Do you have that on yours anywhere? They're called
yeah, the
they're called
optional practice.
optional student practice. My understanding is that these are supposed to be exact, and I thought I opened those up for you guys.
Yeah, okay, I see those.
Can you
I was
access?
just looking under the my assignments part, not the.
Can you actually open those up or not? Because I've heard different things for different people that. When I say people, I mean people at College Board, that you have to have the lockdown browser, and I don't know. So I'm going to try to see if I can open this one, because I did one time. See if I can open it again. This is what it should look like as soon as it loads here. So there's one like this car on this hill.
Okay.
And so that's one that they say should be really good practice for the test.
Okay.
And okay, where's the other one at? Okay, wait a second. So I thought I've opened them. Okay, so there's those. Oh yeah. Okay, so here's another one here. So this should be a different one. Click this one. And I'm going to talk more about this. In fact, I was kind of hoping on Thursday that I was going to be able to do all this kind of with you and show you where these are. And I'm going to kind of assign you guys to do these over the weekend. That way we can talk about them next week. So the next one kind of looks like, I don't know, what is this? It looks like maybe a dart hitting some object. My guess is that it's probably going to go flying off. You might have to do some kinematics, projectile motion kind of stuff. They said this is another excellent one for practice.
Okay.
And let's see if I can find that other one. Let's see. So the two long ones are, so there was two long ones they said that we were having access to, and then a short one. The truth is, the short one, we won't have to do anything with springs, harmonic motion. So I don't know how good of a practice this one is, because I remember I heard some people complaining about this one, but at least if nothing else, you can see what the format looks like of how you're going to type or upload answers. If you still want me to open up some of the other, how do I get out of this? Okay, so maybe I just click over here. Oh, there's the X. If you still want me to open up some of the other progress checks or something, I can do that. It's just I didn't want students to come in here and be overwhelmed with stuff. I just wanted them to see, oh, this is exactly what the test is supposed to be like.
Right. Yeah, no, I would still like it if you would open up like the earlier units, because
Are you sure you want me to do that? Because I feel pretty confident that you should be okay with those. I'm more worried about Unit 5, but I'll
well,
open
yeah, no, especially the Unit 5 ones really is what I was thinking.
Okay.
Just because I want to get like, I don't know, we've been working on like a whole bunch of FRQs and calc through my AP, and I thought those were really helpful.
Okay.
Because it gets me used to like how the questions are being asked and like what work I need to be showing to get the points. And then do you have access to the answer keys? Because I know that my calc teacher does, so she posts the answer key so you can grade yourself.
How does she post it? Does she post it in the classroom or where?
She puts a link on Canvas.
Okay, so I'm not doing that because that's not I'm not doing that because I don't want to get in trouble.
Right.
That's the College Board is very particular about that kind of stuff. This is what I'm willing to do is that, again, next week, I'm willing to actually show you the answers. I thought maybe in here you could actually see them yourself, because I'll show you right where they are from my vantage point right here. It says scoring guide. Do you not have that on yours?
No,
So
we don't have any of that.
I can click on the scoring guide and it will, so it will then pull up this PDF. Yeah, okay, that makes sense why they're not sharing it with students, because they don't want students to have any of this stuff. They're very close to the vest with their cards. They don't want students to have this stuff. But I will definitely, they said that I could make a video and talk about it in there, but I'm not allowed to share this stuff or push it out on the web.
Yeah, okay, that's fine.
Okay, so I was planning on doing that next week, but again, how do I get out here? Okay, so you would like me to open up some of the other progress checks then?
Yeah, just for
okay. So
practice.
So what other units? Like, let me go through the units. So like there was kinematics, there was dynamics, there are forces, there's energy. I mean, I can open them all up, but I don't want you to feel. This is what happens when I open up everything I've known. I've seen it in the past. What happens is students get so overwhelmed they don't even try to climb the mountain. So.
I'd be fine if you opened up everything, just because I would pick and choose what I needed then.
Okay, all right.
But I mean, I guess mainly with like Unit 5 for sure.
Okay, yeah, I agree. Okay, I'll do that.
Yeah. All right.
Okay.
Thank you.
Yep, no problem. All right. Krishna,
Bye.
did you have a question? Bye.
Yeah. So for internet homework,
Yes.
I looked at it and it was like all of the questions were like really hard, and it was talking about like radians and stuff.
Oh, well, you know what? Look, do you have it open? I haven't looked at it yet. Honestly, I haven't looked at it, so you might not be able to do 6. I need to kind of look at it. If you have it, it'd be great if you'd share it with me, right? Or, share your screen with me, and then I can look at it. And yeah, there might be a possibility that it's not going to be 6 that you do. Maybe it's only 2 or 3 that you can do. So.
Yeah, I'm opening it up right now.
Okay. And then as soon as you open it up at the bottom, if you can hit the green share your screen